In this video, we're going to take a look at some of the Pwn challenges from the HackTheBox Synack RedTeamFive CTF, which is running this weekend. So we'll start off with this injection challenge based on the number of solves. It's got 32 at the moment, and the description says there's a guard in front of the door. You need to hurry up and inject him so that he falls asleep. So we've got a server to connect to because it's a Pwn challenge. Each one of these will have a Docker, so I'll launch that to begin with, but we'll go and try and get things working locally first of all. I've already got the file downloaded here, so we can have a look at it here. It's a 64-bit LSB Pi executable. It's not stripped. Let me also run checksec, and then I'll explain a bit about that. Here's the security protections which are enabled. So the Pi executable, which we can also see here, just means that every time the program loads, it'll have different addresses for the functions and, well, for everything. So we'll only know what the offset of each function or variable or whatever is. We won't know until the program's actually running exactly where it's located. It's not stripped, which just means whenever we're reverse engineering it, we'll be able to see the function names and things like that. And then some of these other protections we have, well, let's focus on NX, which NX is disabled, which basically means if we're able to inject some code onto the stack, we'll be able to execute it. If this was enabled, it basically means that data is either marked as executable or as data, so you can't just inject code and expect it to execute on the stack. There are no canaries, which means if there's a buffer overflow and we exploit the buffer overflow, we won't need to worry about tripping off any canaries. These canaries are basically set at the beginning of a function with a random value, and if that value is overwritten, then it'll come up with a message saying stack smashing detected. And the rel row is just to do with the readability and the writability of the global offset table and stuff, but we probably won't need to worry about it for this challenge. So let's go ahead, let's make the file executable, and let's just try and run it first of all. And see, it asks us here, do you see the guard over there? Do you need to sneak? You need to sneak and inject one shot or the shot in order to make him sleep. Can you do it? So if we say I do not think so, we just get mission failed. If we say yes, we get this address which is leaked. So let's actually just try that again and see. So you can see this address is different each time, and then it's asking us for some input, so we might want to try and put in a long input here to see if we crash the program. And we did. We got mission fail, but we also got a segmentation fault, so there was a buffer overflow there. So we'll have a look to see where the offset is in GDB. I'm not going to do that for every challenge. I'm just going to show a couple of different ways we can do this, but let's go and have a look at this in Geardra first of all. So in Geardra here we've got our functions on the left where we've got our main function. We'll go and have a look at this, and we can see we've got this buffer defined at the beginning. So we've got an int variable 2c, and then we've got this buffer of 32 bytes. We can actually see the stack layout here as well. So based on this, based on this value here, we would expect it to be 40 bytes for us to overwrite the return address, and we can see that here. So the stack for our local 28 variable, you can see we have the hex 28 there, which is 8 and then 2 times 16, so 32 plus 8 is 40. So we know that our offset in this case is 40, but we'll go and see how we can determine that with GDB as well. We then have our print statement, which we saw there. It's going to take some input off of us. It's going to read it into this local 2c variable. Oh, sorry, that's going to take our initial number, so it's going to ask us 1 or 2. We provide 1, and then it's going to provide us this pointer, and the pointer is this local 28. So it's actually giving us the address of our buffer in memory, and then it's going to read from us. It's going to read 279, which is 633 bytes. It's going to read from us. It's going to then put out this mission failed, and then it's going to return. So this is where our buffer overflow is. We've got a 32-byte buffer, and it's reading 633 bytes into it. So let's just go and see how we could check that out in GDB anyway. If we open up GDB-PwnDbg injection shot, we can have a look at our functions in here. So we've got our main function. Let's just try and generate a cyclic pattern. We'll generate cyclic and we'll say 100. We know it's going to be 40 here anyway. So every 4 bytes of this pattern are unique, so we'll be able to find out which 4 bytes end up in our instruction pointer, and then we'll know based on what 4 bytes it is where in this what the offset is essentially. So let's run the program. Let's say 1. It gives us that value. Let's just enter in that long string. See, we've crashed the program, and we can see here then that the value that's made it in to the RIP will be our KAAA. Let's do cyclic-L to look that up. We'll see that the offset is at 40. If we were doing this on a 32-bit machine, it would actually arrive in the EIP, but in 64-bit machines, because it's not KAAA is not a valid memory address, it just won't even try to execute that. But we know that what our offset is now, although we knew that anyway from manual analysis. We can also find that in PwnTools, which we'll show how to do here shortly. But let's just talk about what our plan is here. We've found the buffer overflow. We've found that we've got quite a bit of space there, and we know we're able to inject shellcode on the stack. So we don't need to worry about doing ROPs or anything like that. We should just be able to go and make some shellcode, and we could do that in something like MS Venom, or we could go online and find some good, nice, short, effective, reliable shellcodes. What I'm going to do here is let me go to my GitHub, and I'm just going to find a similar challenge. Once you've done quite a few of these, you'll kind of end up seeing you know, what the challenge resembles based on challenges you've done before. In this case, I'm going to grab the back computer script from the HackTheBox, and normally I just kind of use a template here, but I'm just going to grab this and copy it over. Let's go out of GDB, let's open this up as exploit.py, and we'll paste this in here and we'll go through and modify it a little bit. So we've got quite a bit going on here. Let me just explain a little bit if you haven't seen any of my Pwn videos before. So this is a template I use which has a start function just to make it quite easy to swap between locally running this, remotely running it, and running it with GDB enabled. And we can also set up some breakpoints and stuff here for our GDB script. We have a find instruction pointer function. So at the beginning, like we went and found that instruction pointer offset was 40, we could just type in here 40, but instead we've got a find IP function which is going to do that for us. And you can see here a little bit of this is going to need to be modified. So we know that it asks us to enter in a 1. That's the first option we provide, and then the next thing is going to be we send off that payload, and then that's going to be it in this case. So if we run that, that should be good. I'll just comment this out quickly, and didn't comment out, there we go, okay. And we also need to set the binary name, so we set the binary name here as injection, and basically here this is going to find out what architecture this is and the other properties that we need, so that we don't need to worry about packing addresses and stuff later on. And then we're just setting up our login level here, which we can swap between warn and info and debug depending how much information you want to show. So let's try and run that. Python exploit, no such file. What's the file called again? Injection shot. Okay, so run that again. And this time it's run through, it's found out that the instruction offset, the RIP offset is at 40. So it basically ran through, it tried to crash the program, and then it's found out what the offset is based on the core dump. And now we can go ahead and just use that in our exploit. So let's, okay, I'm just going to uncomment that, but let's uncomment that, and let's make some other changes that we need to make. So this is fine. It's just we're gonna enter in a 1, and that's going to return the stack address for us, which should be fine as well. I've got some regex already to do that from the previous challenge. This was needed for the back computer challenge because there wasn't enough space on the stack. I'm going to take that out though for now. I'm also going to change this to the shellcode. Let's first of all just try and get it working with a shell. So this shellcraft, normally you would need to type in here like shellcraft.linux.x64, but because we have set our context up here, it'll take care of all that for us. All we need to do is put in sh, and that will get us a shell. And then we have here our padding equal to, so basically our plan of action really here would be to inject the shellcode onto the stack and then overwrite the return address with the address of the stack that's leaked to us. So then it'll jump back to the start of the stack and start executing our shellcode. Obviously, if the shellcode doesn't take us all the way up to the instruction pointer, we would need a bit of padding in there just to make sure it makes it up to 40. So that's basically what we'll do there. Let's just build up the rest of the payload. It's not going to ask us for a password here, so it's just going to send the payload after this, and that should be fine. We'll just jump into, I'm going to comment this out, but we'll set that up later, and we'll just try and jump into a shell to see what happens. What I am going to do here is just print out the length of the shellcode. So let's try and run it. We run through that, we get an end of file error, and the length of the shellcode was 48. So the problem there is, even if we take out this padding, it's gonna be 48 bytes, and then it's gonna overwrite the return address. So we need 40 bytes and then our stack address. So the way that I got around this was to, we can say here, let's just say our padding is equal to, padding times ASM nop. Our padding will be up to our, let's do offset. So our offset is 40, that was what we calculated up here. And the offset is going to be, we're going to do 40, no operation instructions. And then we're going to do our overwrite the return address with the stack address. But we don't want it to jump back to the start. We want it to go to the shellcode afterwards. So we know that the stack address is pointing to the beginning of this buffer. And the beginning of this buffer is 40 bytes away. So let's do stack address plus offset, so plus 40, and then we also need to do plus 8 because the stack address is 8 as well. And then that's basically gonna, so this is gonna jump essentially to this shellcode here. Hopefully that makes sense. Let's take out the print of the length there. There's some other ways we could have done that. We could have gone and found some shorter shellcode as well. That didn't work for me. Let's go back. Oh, I'm still sending a 1 here. So we sent the 1 already up there. Sorry, that's my bad. Let me run that again. We run that again. We get our mission failed, but we see that we actually have a shell down here. You can see because we've got a debug mode on, it's showing all that stuff in the background. We can now run ls and who am I and stuff like that. So if we were to run this against the server, it should just give us a shell. What I'm going to do though is just go and modify this. We want to grab a flag.txt. So I'm going to echo fake flag to flag.txt, and then I'm going to change this exploit slightly. Instead of doing shellcraft, let's do cat, well, we're still doing shellcraft, but we'll do cat instead of shell. So we're going to cat flag.txt, and then we're going to grab the flag here, and because it said came up mission failed at the end, we need to just grab another line from it. So we're just going to say io.receiveLine. That'll receive the mission failed line, and then after that it'll grab the flag for us. So let's try and run it again, and we get back our fake flag at the end. So the cool thing now is that we can just go ahead and run this against the server. Let me change the debug mode to info, and let's go and grab the remote server address. So we can just go and take a copy of this. Because we're using this kind of template, we can just run the exact same script, Python exploit, but we just type in here remote in capital letters, and we paste in the address and a port number, run it, and we get back our flag, HackTheBox, shellcode injection, done. But we could easily do that as a shell or something else as well. The next challenge is called library, and the description says agents have the privilege to access our secret library and search whatever they need for their missions and training. Pay a visit. So I've already got the server booted up and downloaded the files. In this case we have a binary called library and a libc library as well. So we can run checksec again and see what's different compared to the last binary. So we'll run that against library, and we'll see that it's still got full railroad, there's still no stack canary, and this time it has no pi, so the base address of the binary will be at this address each time, and NX is enabled this time, so we're not going to be able to inject shellcode onto the stack basically. So that's a hint that we'll probably need to look at using ROP gadgets to return to the libc library which has been provided and execute like system or something from there. So let's go over to Geardra and take a look at it. if we go over here and have a look at our functions, we've got our main function. Really not too much going on here. We've got a 32-byte buffer again, which we could go and determine. We can determine that here. We could go and check it out manually in GDB, and we can do it in PwnTools. I'm not going to go through all the steps again because I did that in the last challenge. But it then reads in, it says salute, are you here to look at the book? And then it's going to read in 60, which is 128, is it? Or 96 bytes into a 32-byte buffer, so there's obviously a buffer overflow there. The problem is that we're not able to just insert some shellcode, so our goal in this case would be to first exploit this buffer overflow, and if we go to our global offset table, this is where we have our libc functions, and basically if we can print out the address of one of these functions in libc, so just a little bit of background, so libc will have different addresses and offsets on each version, so people's systems will all be different, and this just means that whenever you run this binary on your local system, rather than including read and puts and printf and all those functions in the binary and making it really big, instead it will link to those functions in your libc library. But because those functions are in different places, in different libc libraries, it needs to first populate this global offset table with the address of the function in libc. So the first time it's called, it'll basically populate this address, then the next time it'll just go and look it up from the global offset table again. So what we can do is try and leak an address. It doesn't matter which one. We could do puts, printf, alarm, read, and we want to leak it, and then once we have that address we can calculate the offset to any other function in libc. What we would typically do is calculate the offset back to the base of the libc binary, and then from there we can quite easily get the offsets of all the different versions. So we would do that first of all, leak our address, and then we would tell it to basically go back to the start of the program, and then we'll overflow this buffer again, but the next time we'll use our leaked system address to call bin.sh, which we can also find in the libc library. So as with the previous challenge, it's quite easy to find, when you're looking at kind of challenges like this, it's quite easy to find examples from previous CTFs. So let me go back to my GitHub. There's quite a few I could actually use here, but specifically I remembered that there's one called the library. You can see this also, well, I created 3 files for this. Let's start off with this local.py. We'll go and take a look at some of the others as well though. And let's create then exploits.py. We'll just go and paste this in. We'll go and update some of these values in here. So it's called library instead of the library. And if we run the program, let's try and run it. We can see that it gives us that little angular bracket and then takes our input, which is where we can overflow the buffer. So we want to update our instruction pointer function to find where the offset is, which is going to be 40. We could just type in 40, but we'll let it do that for us automatically. And so we need to update anywhere else. Let's see. We have this pop RDI gadget. You can see that's hard coded from ROP. So let's go and do ROP --file library, and you can see that we have this. There's a rec gadget. Sorry, not a. We need a pop RDI gadget. We can see right here. So I'm just going to go and update that address. And let's talk through our payload. So the reason I'm able to reuse this script quite easily is because of the way this has been set up, because I haven't done, this is the only address that we set manually. Everything else you can see we've kind of used function names and stuff. So this is set to my local libc library at the moment. What I'm actually going to do, what I'll do is update this one as well. Libc, it's called libc.so.6. That's the remote version, so we're basically given that version and told this is what's running on the server. So you could actually set up like the LD preload to make it use the same libc on your local system as on the server. I typically just swap between the two of them, which seems to work okay for me, but let's talk about the first payload anyway. So we've got this first payload, and we have a pop RDI, so the first gadget is going to pop the next value into the RDI register, which is going to be the global offset table puts function, and then with that in the RDI register, it's going to call elf.plt.puts, And basically that's going to put out to the screen anything that's in the RDI register. And what's in the RDI register is that address that we want to leak, that global offset table address. So it could be printf or something else, doesn't really matter. And then we want to go back to the main function. So just to go over that again, we're overwriting the return address with this chain of ROP gadgets basically. And it's going to go through each one, it's going to leak out our global offset table address, it's going to go back to the main function. And then we're basically going to format this, we're going to get our leaked address. Let me just kind of go through this in steps. Let's try and run that first of all. So we'll run Python exploit. It's going to find our, you can see it's sent off 1,000 bytes. It's found our return address offset, which is at 40. And then you can see down here it's sending off our first payload. And the first payload, we've got our 40 bytes. We have then our address of the pop RDI. We have our address of the global offset table puts function, etc. And it basically then returns this, and you can see that at the end, was it the end or the beginning? It returned our address there anyway, our global offset table puts address. And from there we can go and calculate the offsets to other addresses. So we can go, you can see here basically what we've done is we've set the libc address, which is our libc library up here. We've set the libc base address to equal the global offset table puts address we just leaked minus the libc symbols puts. And this means that from now on we can just say libc.system, libc.printf, etc. and it'll know where all those are because we've loaded the binary. We can also search for the bin sh string in there. We could do all this stuff manually as well. Let me just actually demonstrate what happens if we, let's run this with GDB. So I'll run this again, I'll just type in GDB in capital letters. Because I'm using this template, it's going to open up GDB. It's going to run through that. We've got a break, I actually set a breakpoint at main there, so you can see in our GDB script we've got a break main set. So let's just hit continue. It continues, it goes through to the end, and we've got our leaked addresses here. So what we could do is we could go and just verify these are pointing to the right thing. So you can see that's pointing to our puts, which is what we want. We could go back and make sure this is pointing to libc base. Okay, we can go back and check our system, libc system, and then bin sh as well. X, that's a string, so we'll represent it as a string, x/s. You can see that's bin sh, so everything's correct as it should be. And this can be quite handy in terms of debugging, where if you have some offsets wrong or if you're leaking your address incorrectly. We can also search in here, so we can search like search-s for string and bin sh, and that'll actually find us the address as well, and we could go and calculate our offsets in here doing the same sort of thing. But that's how that works anyway. I think let's just try this out. This is our local libc library, so let's try this out and see if it works. Python exploit, it runs through, we don't get an end of file, which is good, so we hit ls, we do who am I, and we have a shell. I didn't actually explain. So okay, so we leaked our got puts address, we calculated the offset to our system, we got our bin sh, and then our second payload, we're popping the bin sh into the RDI register, and then we call system. So system will basically look in the RDI register and see what am I executing, and it's going to execute that bin sh string. So that could be something else, it might be catflag.txt, but catflag.txt doesn't exist as a string in the libc library. So you'd need to find that somewhere else, so you'd need to build it or write it somewhere. But bin sh is obviously, I mean, that's the typical goal anyway. So I'm going to modify this slightly just to make this a bit easier between swapping between local and remote. So we have this libc is being set here. What I'm going to do is set this to no, actually we'll just leave it. I was going to say we could go and modify the start function so that whether you select local or remote will depend what libc library it sets here. What I'm going to do is just comment this out, and that's basically us set to now use the local version. So if we run this again, we're not going to get a shell. because it's using a different offsets, so all these addresses aren't going to match up with our library. If we wanted to test this against the server, by the way, if we wanted to try and find out what libc version the server is using, in this case we don't need to because we were given the libc version, we were given the libc file. But if we weren't given the file, we could just leak the, say, the puts address from the server, and then we can go and say in here puts, and we can just do puts and then just put in the address that it gives us, and then that'll give us some potential options. So let's actually try it. Let's run this, get the server address and port number. We run it remotely, and okay, so where's the, okay, so here's our leaked puts address. So we take a copy of that, we can go and put it into the libc database, hit find, and that will find us all the potential libc versions. In this case there's only one, and then we can go and find out what our offsets are. So if we were doing things manually, we could just go and manually type in these offsets. But if we want a reusable script like I have at the moment, which we can easily then just apply to different libc versions, I think it's a lot better to set up libc in this way. But that ran anyway. It didn't actually get us a shell, and the reason being, I think, is because we need a it's a stack alignment issue. So remember I looked for I was looking at the return instruction earlier. Let's try and grab this return gadget. It basically needs to be 16 byte aligned, so we'll say here ret equals 0x, paste that in, and then just down here we want to add in a ret instruction. Do I add it in here or after? Let's see. I'm not too sure it matters, to be honest. Run that, and then we get our shell. We can now go ahead and cat our flag.txt, and that's that working. Just before we move on, let me just show how we can really automate this. So I'm just going to take a copy of the script. I'm not explaining this in too much detail. I always explain this in my Pwn videos, but just in case people haven't watched my old Pwn videos, and some of the audio quality is probably not as good on them. Although the audio quality is probably a bit hit and miss on these as well. But yeah, so what we can do here is create a ROP object here. You see we've created ROP elf, and this is a class which will simplify the generation of ROP chains. And compared to our last code, remember we had all that code together where we were saying pop RDI, and we were popping the puts address in there, then we were calling plt.puts and etc. This time it's just going to resolve all that for us. So we're just going to call rop.puts, and then we put in the parameter that we want to put, and this is going to do that whole thing for us, and then we're going to return to the main function. Let's actually pprint rop.chain. No. Yeah, let's try that. I think that's a way to do that. I'm going to comment some of this out. In fact, no, let's just do that, and let's, oh, rop.dump, there it is, sorry. That will basically just print out the whole chain that it's built for us. Just want to kind of visualize that. So we're just going to send that off. So at the offset, we'll send off our rop.chain. We then leak our address, we update our libc, and then we can update our ROP object to now point to libc, and we can just call rop.system and search for the bin sh string. We did need a ret gadget in there as well, by the way, to get that to work remotely. But let's try it anyway. Let's try it locally first. Locally, we get an ender file. Maybe that's, do we have the libc? Okay, set to the remote libc. So we test it with a local one first of all. It's leaked our address. It's given us a shell, that's great. And if we go and have a look through our debug here, we can see that it's generated our, this is the rop.dump. So whenever we've called rop.puts and rop.main, it's built up this chain for us where it's found the address of pop RDI, it's found the address of the got.puts, it's found the address of puts, and then found the address of main, and it's done all that for us. And then again with the system, it's found the address of pop RDI, it's found the bin sh string and put it into the RDI, and then it's called system. And again, that's given us a shell. If we run this remotely as well, it's not going to give us a shell because we have the wrong libc library set there, but if we update our libc and run that again, and you can see now we've got the flag again. On to the third pwn challenge. So I'm doing these in order of the number of solves. So we start with injection, then library, and we'll move on to recruitment. What's interesting is recruitment is actually the easiest challenge here. It's a classic return to win style challenge. So it just goes to show that the number of solves isn't necessarily everything. But anyway, the description says we're looking for some skilled agents to train in order to make the greatest spy army in the world. We need your info in order to join us and give you an agent ID. So we've got a server to connect to. Let's get that booted up so it's ready. And let's go and try and get this working locally. So as usual, we'll run checksec and see what protections are enabled. This is the same as the last one, so there's no pi, NX is enabled, no canaries, and full rel row. Let's just go ahead and try and run the program. And it asks us for some input. We can try and enter in a large input here, and that's okay. We actually overwrote, you can see the agent ID, but we didn't crash the program. Let's try a bigger input, and this time we get segmentation fault. Okay, so that's what we would expect. Let's go over to Geardra, open up the functions. We've got this main function, and I guess this is maybe here just to cause a little bit of confusion, but this random stuff doesn't actually mean anything. So we have this time in, we have our buffer of 44 bytes, and we have the local C here as well. So you can see this is being like randomly assigned the agent ID, but it doesn't actually have anything to do with the exploit. Where the exploit is at this read. So you can see that we're reading in 40, which is 64 in decimal. We're reading in 40 hex bytes into, or sorry, 64 bytes into a 44 byte buffer, and that's where the vulnerability is. The thing is, where do we want to return here? So in our previous example we did a return to libc attack, and before that we injected some shellcode. We can't inject shellcode here. We could potentially do a return to libc attack. I don't know if there's enough space. There's probably not enough space actually with the overflow. But if we go and have a look at some of the other functions here, we have this function called agent ID. Normally this would just be called win or flag or something like that, so I guess a lot of people have probably overlooked it. But what this actually does is it opens the flag and it prints it out. So if we can redirect the execution of the program from this main function to this agent function, which is never actually called, if we select here references, show references to address, there's no unconditional calls to this. So yeah, all we need to do is write however many bytes it is, like 56 bytes I think, to the buffer, and then the address that we want to return to, which in our case is going to be the agent ID address. You could specify that manually, just go and grab this address here and copy and paste it, or if you're using PwnTools we can go and say elf.symbols.agentID or elf.functions.agentID or something. And that's about it. So let me copy over the PwnTools template. I'm just going to grab this from my CTF directory, PwnTools, no, where is it? Official template. Let's call it exploit.py. And we could actually do this completely manually, this challenge. Let me create a fake flag here. Let's do echo fake flag to flag.txt because we know it's going to try and open that up. And we could open this up. Let's do GDB-PwnDbg, what's the file name? Recruitment. We'll generate our cyclic pattern of 100 bytes, take a copy of it, run the program, paste that in, and we overflow. We can see that we've got these 4 bytes here at our RSP, so let's do cyclic-L to look that up, and there we get 56. So if we were doing a payload manually here, we could say Python 2 because Python 3 will cause some problems with the bytes, and we could say print a times 56 plus, and then the address that we want to jump to. So we'll go back to, we get that from Geardra, we get it from Radare, or we can get it from PwnDbg as well. So let's do disassemble agent ID, and we can see that we have this address. So we need to put this in little endian format, which basically means we'll do it in reverse order. So \x22 \x09 \x40, so each byte is in reverse order. And then we also need some padding as well, so \x00 \x00, we'll do that 5 times. I'm going to take this out. We print that, and it's not in a recognizable format. We need to send it to a file like payload. And then if we just try and run recruitment and send in that payload, you'll see that we've printed the fake flag. So that's one way we could do this. We could also try that in GDB. We can do run and send in that payload, and you'll see it prints out the fake flag there as well. But let's go to our PwnTools template. Let's go and update this a little bit so we have that function looks okay for finding the instruction pointer. Let's update this to recruitment, bearing in mind I think they spelled recruitment incorrectly. And let's go and put together our payload. So at the offset, we're just going to say we want to jump to elf.functions or elf.symbols. Oh, can't spell. .agent_id. And that's literally all we need to do. We'll write the payload to a file because we might want to check it later. We could also do this instead of IO interactive. Let's do that instead. Let's comment out IO interactive. Close this down. Let's do Python exploit. We run through that. Okay, that didn't actually work for us. I think we might need to receive a line here first. IO receive line. Try it again. And okay, there's quite a lot of stuff there. What I'm going to do is we'll just do IO interactive. You could work out how to format that correctly if you wanted it. Just have a nice clean looking output. But we do that, we get our fake flag, which is awesome. Let's just go and test this out remotely then. Grab the server and a port number. And whenever I was trying this remotely, actually it wasn't working for me. We'll try it here now and see what happens. Yeah, it doesn't actually print the flag here, and I was thinking it was to do with the stack alignment on the server. But if we try to add a ret instruction here, if we go and use ROP and grab the ret instruction like we did last time, it doesn't fit the buffer, I don't think. I couldn't seem to get it to work locally or remotely in doing that. Luckily, we can just use the payload. So if I just run Python exploit again, we've got a payload here, cat payload. There it is. We also got that payload manually we could have used. So that just means that we can go and instead of using our Python script, we'll just say netcat, and then we'll just send in the payload. The final Pwn challenge is called air supplies, and the description says, "Agent, you need to drop some supplies to nearby villages in order to help our fellow allies and our all innocent villagers. Make sure you know what supplies to drop and to which village each time." So we've already got the server booted up and we've got this downloaded locally. Let's go and do our usual check sec, see what protections are enabled. And we have a canary this time, so NX is enabled, so we're not going to be injecting shellcode onto the stack. We don't need to worry about pi. There's no rel row, so this is the first case where we've seen a canary and we've seen no rel row, and this relates to the writability of the global offset table, which means we might need to well, the canary is either an indication that we need to leak a canary and overflow the buffer and overwrite that canary, or maybe that we just don't overflow the buffer at all, so some other kind of exploit. And because we have no rel row, that's an indication that we're probably going to be overwriting something on the global offset table. So let's try and run the binary anyway. It asks us, are you informed about the mission? We'll say no. Alright, we need to be informed before we start. Let's do it again. And it asks us, insert what kind of supply to drop, and then insert a location. And we got a segmentation fault. So there's not too much to the code. Let's jump into Geardra and see what's going on. We can see in here then, if we go to our main function, we have a setup, which isn't of much interest to us, setting up an alarm and stuff like that. The alarm, potentially you could overwrite the alarm in the global offset table. So if you were, the alarm I think goes off after like 2 minutes. So if you were to overwrite the address of the alarm function in the global offset table, it would mean whenever that alarm trips, it'll go and look in the global offset table and see what's the address of the alarm in the libc library. but instead of seeing the libc address, it'll actually see the address that we've overwritten it with. Yeah, so let me go into the menu here. This is where it's asking us 1 or 2, and invalid's not of interest to us, so we want to go into choice. Notice we have the stack check fail as well, so we have this canary which is set up at the beginning. It's assigned basically a random value each time, and at the end it's checked to make sure that it still equals the value it was set at the beginning, which means if we overwrite the values on the stack, we're going to need to make sure this is the correct value. So we'd have to leak this value and overwrite it with the correct one. Actually, we did a challenge like this a week or 2 ago on the Killer Queen CTF, so if you go and check that out if you're interested in seeing how we can leak the canary. And we can go and see the canary if you go into GDB-PwnDbg and let's set a breakpoint at main, run the program, and then we can actually go in here and say canary, and this should try and find out where the canary is, and that'll help us identify the offset to it. But it's actually not relevant for this challenge. That's not what we're going to be doing, so let me close that down. It took me a little while to work out exactly what to do here, because if we go into our mission, there's quite a bit going on here, but essentially it asks us to insert the type, the kind of supply drop, and then the location. And the idea here is that it's providing us the first value that we're basically going to say where we want to write to, and then the second value will be saying what we want to overwrite it with. So what I was a bit confused about there is I thought there should be some kind of win function, and it took me a while to find out that there is. So if you have a look here, we've got an underscore function. It's just called underscore, but that actually will open flag.txt. It's going to cat flag.txt. So let's create a flag locally as well. We'll do echo flag to flag.txt just for testing. And let's open up Radare as well. We'll open up Radare. We can do AA for all checks, AFL to have a look at the functions, and if we wanted to, we could do smain and PDF to disassemble and have a look through the code. So you can see here where the canary is being set and where it's being checked at the end. But what we're interested in here is the sections. So if we do I_S to list the sections, we can see what's readable, what's writable, and we could potentially write over, as I say, the alarm and the global offset table. Another option here is we have this .fini array, which if we look up the information about that, we'll find, I actually found this from a previous write-up, that the runtime linker executes functions whose addresses are contained in the fini array section. These functions are executed in reverse order in which their addresses appear in the array. The runtime linker executes a fini section as an individual function. If an object contains both fini and fini array sections, the functions defined by the fini array section are processed before the fini section. We have an address here. This is the address of the fini function, and what I'm going to do is I'm going to take that to ASCII to hex, or you can take it to CyberChef, or you can do this in your terminal as well if you have like unhex. Let me actually see if it comes with the same results. Let's convert this. Oh no, we want it in decimal actually, so let's grab the decimal here, and we're basically going to say then we want to overwrite. That's the first address we're going to provide. Let me actually go and open up Sublime or something to keep track of this. Alright, so that's our fini section, and then we want to overwrite it with our win function, which we could grab from Geardra. We could get it from somewhere else as well, from plenty of places, but essentially we want to grab this function here. Let me actually go back to AFL, where is it? The underscore. Oh, that's weird, I'm not actually seeing it there. Okay, well, I'm probably just being blind. Well, it's here anyway, so we can grab a copy of this. I've missed the F, but that's fine. We'll just paste it in here, add the F on, convert it, and this is the address we're going to write. So we're going to overwrite the fini array with the address of the win function. So if we take a copy of this fini one first, we'll close this down, run the program. Yes, we're ready. Insert that in decimal, and then let's go and grab the win function that we want to overwrite it with. Insert that, and there we've got our fake flag. So with this running remotely, if we just grab a copy of that and do nc connect with netcat, let's just grab our addresses again. So we'll say yes, we're ready. And because these addresses are hard coded, because Pi is not enabled, it means the server is going to have the same addresses. So we run that and we get back our flag. And yeah, that's how we can solve that one. Let me actually just copy it over. We can also do it quite easily with PwnTools. I'm not going to type out the whole script, but if we just want to take a look at this, we'll paste this in. And essentially we just have we just send in after the line, so we're saying yes, we're ready, and then we can grab the init array address from our elf.symbols, and the same with our win function. So if we run Python exploit, that'll give us our fake flag, and if we run Python exploit remote, take a copy of the server address and the port number, and that will also give us a flag. So that'll wrap it up for the Pwn challenges. I hope you've enjoyed this video. I'll leave the scripts and stuff on GitHub if you want to check them out. There's a PwnTools template on there as well. And I'm currently 25th. I suppose I'll go and have a look at a couple of the easy crypto and MISC challenges maybe. But I don't think I'll do any more videos anyway. But any questions or comments or any tips or tricks for me, let me know down below. Thanks.